Hello, and welcome to the second video of the Cal Poly ITRC's Fertigation series, sponsored by CDFA and FREP. This one is going to deal with basic fertilizer chemistry and vocabulary. As a reminder, we have two books for you to take a look at to supplement these videos that you'll look at. And one is in English and one is in Spanish. And you can see the web address here. It's www.itrc.org and then /books. But if you go to the ITRC website, you'll find it just fine. Chapter 1 provides an introduction to quite a few of the topics contained in the book. And I'm not going to read everything that's in the book, but this first section right here does list a number of things that I may as well just put on the screen. First of all, there's the idea of chemigation versus fertigation. Chemigation really denotes any type of chemical that you put through, and I suppose it also includes even solids like gypsum, but it incorporates insecticides, pesticides, fertilizers, and so on. And the focus of this book, though, is on fertilizers, and the primary interest of the FREP program is on nitrogen fertilizers. But anyway, if you take a look at this, it says it's the application of any chemical through irrigation water. And then there are a number of reasons to do it. And I think a lot of farmers in California, at least, and also in the United States, are somewhat, if not very well aware of many of the benefits. You don't have to drive your tractor through, so you avoid soil compaction. You don't damage the roots, as you're going on through with the chemical application that's on wheeled vehicles. And then really less equipment may be required. Notice the may. The may's in there because as we get more sophisticated, we actually don't have just one device like a tractor. You'll have multiple injectors, and you have a flow meter. You may even have a programmable logic controller that measures the flow rate of the irrigation system and the injection rate of the chemical, and then adjusts the chemical injection rate. So we go from very simple to fairly sophisticated. There is less energy expended during application if you do it correctly. Pay close attention to the section on the Venturi injectors, because a lot of people inject inject the fertilizer through Venturi injectors incorrectly. I know that's how I started out years and years ago, about 50 years ago, where we didn't know better. But now we know that you don't run the whole flow through a Venturi injector and drop the pressure by 15 to 20 psi. Then usually you have less labor, and there are a lot of ways to skin a cat on that one. If you have a good irrigation uniformity, you can apply the nutrients much more uniformly than you would with a tractor, believe it or not. And then you can also get them down into the profile because a lot of the chemicals move with the water. And then a big thing here, this is where we're really going, is the idea of spoon feeding, or at least doing incremental application of some of the nutrients throughout the season. It isn't so important for phosphorus, for example. It is important, but not as important as for nitrogen. And that'll be discussed more later. But the other thing is when a crop gets tall, when it gets past what we call lay-by, where you no longer can drive a tractor through it, you just can't apply nutrients with a tractor. So we put it through the irrigation system. So that's a quick introduction to why people do it. Now with nutrient needs, this is a huge topic, and we have several chapters in the fertigation books that deal with this, and there are many excellent books available just on the general topic, and then you can get good detailed information for specific crops. What I'm going to try to do here is hit the highlights so that you have some basic information. The fact is, most farmers are not chemists, and a lot of them haven't had a whole lot of chemistry background. And so I'm not going to attempt to make you an expert on chemistry, but hopefully this will help out. First of all, we sort of categorize nutrients into three groups. There are major elements, and if you notice, nitrogen is a big one. If a farmer's going to inject anything, it will be nitrogen. and then they generally move on to things like potassium and phosphorus. And then there are the minor secondary elements, and farmers may or may not apply these. It depends on the sophistication and the soil and that sort of thing in the crop. It's very common for farmers to apply some micronutrients, and there are a variety of ways you can do this. Micronutrients are found in a couple different forms, and the form impacts, well, first of all, it impacts the cost of the micronutrient, but for example, if you buy chelates. But anyway, you can put this in the irrigation water, and we have chloride, boron. Boron is a bad one also if you have too much. This one where you have to dance between too much and too little. Molybdenum, copper, iron, manganese, and zinc. And so what are really common are the, I'd say the last four: copper, iron, manganese, and zinc. They're quite commonly applied to the irrigation system. Nitrogen is the big one. As I mentioned, if a farmer is going to apply one fertilizer, generally it's going to be nitrogen. But nitrogen, while it's absolutely essential in large quantities for most of our crops, the management is a little difficult. And partly as a result of that, we do have contamination problems in the groundwater. Nitrogen, the nitrate form of nitrogen is negative. It is not attached to the soil particles, and it's in the soil water. And if you apply too much water, basically some of the nitrate in the root zone will depercolate. That means it goes past the root zone and eventually makes it down to the groundwater. And so then we have what are called drinking water standards. And these are set by environmental groups, and they're based on health concerns. And so this map here shows a map where you have different concentrations. Those are indicated by different colors, and you can see the red and the yellow are not desirable. And there are quite a few areas where there's groundwater in California that has high nitrates. It's not just California. You find the nitrates in Nebraska and plenty of other places in the world. The other thing that I mentioned here on the right is that nitrogen also takes quite a bit of energy to produce. This slide has questions and answers. The first question is, okay, if a plant needs a nutrient, or if it uses a nutrient, do you have to apply it as a fertilizer? And the answer is, well, not if there's plenty of it in the soil and it's available. Those are two different things. As you'll see when we get to potassium, in particular, there may be plenty of potassium in the soil, but it's not readily available at the rates that the plants might need it. The second one here, second question, how do you know if the nutrient is sufficient or available? And there are different terms, technical terms that are used in the industry: sufficient, available, things like that. But here's the answer. One is you take a look at a soil analysis, and I'll talk about that later. But the soil analysis tells you what's in the soil. And then the other is the plant tissue analysis. And as you'll learn later on, the soil analysis, a typical soil analysis where you dig up some soil and send it to the lab, isn't done every week typically. You know, it's done maybe at the beginning of the season. The plant tissue analysis, though, which tells you really what's going on with the plant that day, that's done fairly frequently throughout the season with a lot of crops. So these are all discussed a little later. So now we're back to the chemistry again. Again, if you want to have a decent conversation about fertilizers and nutrition, you have to understand a little bit about the pertinent chemistry. So here are a couple of the ideas. First of all, we have symbols for each nutrient. N, for example, stands for nitrogen. And then there's a charge for each nutrient, and be plus or minus. And then these charges impact how the nutrients are held in the soil. But then actually some nutrients are not held in the soil. So here we are again with a little bit of chemistry, and it may not be the most exciting stuff for you in the world, but it will help you to understand what's going on. Well, I'm not really sure why I call this a little bit of chemistry, because if you take a look, there's quite a bit of chemistry here. And it starts with the most difficult fertilizer in my mind anyway, and that's nitrogen. It's the one that's most commonly used, but it's also pretty complicated the way it switches back and forth in different forms. Nitrate, which you see here, that's NO3 with a negative charge, is one very common form of nitrogen in fertilizers, and it's also the form of nitrogen that's taken up most readily by the roots. Now, if you look at it, the O there is for oxygen, the N is for nitrogen. The 3 in the nitrate symbol indicates that there are 3 oxygen atoms there for every 1 nitrogen atom. And since there's no number with the N, that means there's just one of those. The negative sign indicates that this ion has a single negative charge. Some ions have -2, some have a -3. And then we call this, now this is getting more complicated. First I said ion, and now we say, okay, if it's a negatively charged ion, we call it an anion. And what happens is you get these charged particles, such as nitrate, and it will combine with a particle of an opposite charge. Turns out like calcium is such a charge. It's positive. And it creates a molecule. And that's really what you buy. You buy molecules of fertilizer. The molecules then can dissolve in water. Not all molecules do dissolve in, well, they dissolve, a lot of them, some of them don't. Like there's some phosphate compounds that don't dissolve. Other molecules will dissolve, like sugar, but it's not a salt because it doesn't break into 2 or more charged particles. But a lot of our fertilizers do break into 2 or more charged particles, and that's called a salt. It's just like table salt, which happens to be sodium chloride, and we just have other types of salt. And then the plus or minus charges on the salt always balance out. In other words, if you put fertilizer into a container of water, if you had solid fertilizer and you put it into a container of water, you're not going to get shocked when you put your finger in it. You know, everything balances out. What we have here is a series of questions on different slides, and you can see on the left that you can pause the video after you read the question and think about it before answering it, and then move forward. The following slide after this gives you the answer. So let's take a look at this one. It's just meant to stimulate your brain with some of the ideas that were provided in the previous slides. But this says, okay, one form of nitrogen fertilizer is nitrate, NO3. And the question is, what does the O stand for? The answer is oxygen. So it's not a 0, it's an O. The number 3 is a number, obviously, but the O here is the letter O for oxygen, which is one of the elements. For this one and for subsequent questions, what I suggest you do is just read what's there yourself. And before you do that, just pause the video so you have time to read it. Think about the answer, go back if you need to, and then move forward in the subsequent slides. So this one, of course, is nitrate. It has a 3 in it. What does the 3 indicate? And the answer is that the ion, nitrate ion, or anion, has 3 oxygens in it and 1 nitrogen. The negative sign there, what does that indicate? It's not too difficult because there are only 2 choices, well, 3 choices. It's a 0, it's a negative, or it's a positive. The negative sign indicates that it's an ion, and specifically with a negative charge, and we call that an anion. And then what it means in terms of management is that it is found in the soil water, but not on the cation exchange capacity. And we have a term there on the cation exchange capacity about being adsorbed as opposed to being absorbed. So ad means it's like a magnet. It's attracted to the surface of the soil particles or humus particles by the negative charges on the cation exchange capacity. Obviously, since this is a negative, it's not attracted to negative charges, so it stays in the soil water. So the next one is, what's a salt? Now, to give you an idea, nitrate is not a salt. but at least it's part of one. The salt then is mined as a solid, but it's found in water, and it's a molecule that will dissolve in water, and it divides into two or more charged particles, or ions. And as I mentioned before, the negatively charged ions like nitrate are called anions, and the positively charged anions are called cations. So there's quite a bit here. They're ions, and when you associate a charge with an ion, it's either an anion or a cation, and you don't notice the charges until they're dissolved in water. Next question, of course, is nitrate, NO3 with a negative sign there, is it an anion or a cation? So, and how do you know the difference? The answer is that nitrate is an anion because it has a negative charge. That's the definition of an anion. It's a charged particle and the charge is negative. So a little bit of review on nitrate. Remember, nitrate is a form of nitrogen that's found in fertilizers. It's also the form that's commonly taken up by plant roots. And so here are sort of the ideas. It's a form of nitrogen in fertilizers. It's a charged particle. You can see that. Specifically, it's an anion. And it will combine with other particles with a positive charge. In other words, the opposite charge to create a molecule. And it dissolves in water. And I mentioned that the plus and minus charges in the water always balance out. They aren't, you're not going to get electrocuted. So anyway, if you have nitrate, either in the soil water or as a fertilizer, there has to be something tied onto it, another cation, at least one cation. And that gives you a fertilizer with no charge. And the example given here is calcium nitrate. Now, calcium has a positive 2 charge. And so its charge is offset by 2 nitrates. That's why you have the subset there, 2, the subscript 2, because there are 2 nitrates of 1 negative charge each that combine with 1 calcium that has 2 positive charges. Now the reminder here is that cations have positive charges, anions have negative charges, and one of the co-authors of the first edition of the Fertigation book was Tom Rohr, and I always got a kick out of him. He'd show a picture of a cat with these plus signs on it and then say, well, that's a cat ion. Anyway, I'm not so sure how we're going to get that across in Spanish, but here it is in English. So here are the most common forms of nitrogen that we encounter in the fertigation world. Now there are other forms of nitrogen, like nitrite, but really this is what we primarily deal with fertilizers. The nitrate, that's a single negative charge with 3 oxygens, and I've already talked about that. Then we have ammonium, and if you look a little further below, there's ammonia, and you notice that the ammonium has a positive charge and 4 hydrogens. The ammonia, it's a gas, and it has no charge. And you probably smelled this if you ever used household ammonia, for example, or even if you've been around a fertilizer tank with ammonium, some of that will convert to ammonia and go off as gas. Anyway, the ammonium ion is found in a lot of fertilizers, and for example, there's ammonium nitrate, which has 2 different nitrogen compounds in it. There's a single positive charge on ammonium, a single negative charge on nitrate, and some farmers like the combination of the 2. Each one of those pieces, the ammonium or the nitrate, moves a little differently in the soil and is taken up a little differently, and some farmers have their reason for using this, for example, early in the season. Then there's urea, and that's kind of a complicated formula. But urea is a very common fertilizer also, and sometimes it's combined with the other forms of nitrogen, like UAN32, that's urea ammonium nitrate. And so how's that? You have 3 different forms of nitrogen in one formula. The urea itself has no charge, so that's a molecule that dissolves in water but isn't a salt. And then there is another form that we talk about occasionally, and that's nitrogen gas, which makes up about 78% of the air. It's not a fertilizer. Now, it turns out that there are legumes, certain crops, like peas and alfalfa and beans, which have the ability to take nitrogen out of the air and convert it to a usable form. But we don't apply it as a fertilizer. If you applied N2 gas, it would just go right back into the air. So it's not really a fertilizer at all. So again, you may want to pause the video and read this and think about it and then go to the next slide. But the question is then, what are the 4 forms of nitrogen used in different nitrogen fertilizers? And there was a list on the previous slide of 4 types. And then there was a mention of N2 gas. That's not one of the fertilizers. The answer regarding the 4 forms of nitrogen fertilizer are nitrate, ammonium, urea, and ammonia. I did mention urea, ammonium nitrate, UAN32. I didn't talk much about ammonia gas, but I'll talk about that a little later. And it turns out that the gas, ammonia gas, is often injected directly into soil, that'd be by tractors, or it's injected into water. And it combines with the water, and again you'll see this later, to form ammonium, and it's commonly used in some areas as a fertilizer, basically because it's inexpensive. But as you'll learn, it's not necessarily what you want to use. Again, trying to stimulate the thinking, get those old brain cells working. What are the charges of the 4 forms of nitrogen fertilizer? And by knowing this, it does help you understand how they're going to move and how they're going to make transformations in the soil. The charges here are negative for nitrate, positive for ammonium, and no charge for either the urea or the ammonia. So 2 of them have charges and 2 of them don't. A little bit more about these. I mentioned now nitrate, which stays in the soil water solution, and it can be leached out. It's not attracted to the cation exchange capacity. It's a very common form of fertilizer. Ammonium type fertilizers are generally a little cheaper, and so a lot of people use them, but it's quite different. It has a positive charge. It's attracted to the cation exchange capacity. Then there's urea, which is not directly taken up by the plant roots, but what happens is it goes down in the soil, and there's an enzyme, just like we have in our stomachs. There's an enzyme in the soil that naturally occurs. It's called the urease enzyme, and what it does is it latches onto the urea molecules and then converts them to ammonium, and I'll talk about that later. It's the rate of conversion depends in part on temperature. And then we have the ammonia gas, and we don't usually call it ammonia gas. See these tanks here in this picture? These were taken down near the Colorado River, where it's common to use this, unfortunately. But and you'll find out about the unfortunate in a bit. But we usually call it anhydrous ammonia, this gas right here. And basically it's pressurized ammonia. And what they do is, you can see little hoses coming from these, and someone adjusts the hose, the flow, and they dribble it into the water. That's an irrigation turnout that you can see just above the words ammonia tanks. And the water goes from the canal into the turnout. The gas mixes with the water and makes ammonium. So it's a conversion right there at that level. This paragraph is taken from chapter 10 in the Fertigation book, and it's a little tough to shortcut this one. Basically what you have here is we have 3 different mechanisms for uptake. One is called diffusion. It needs to be explained here in a little bit, but there's root interception and mass flow. So what in the world is diffusion? Diffusion means that you have an area with a high concentration of a certain chemical, and it's in liquid. It's basically the soil water where there's a high concentration. And then it will move from an area of high concentration to low concentration. In other words, if the root is taking something out of solution, that creates what we call a gradient. And so the nutrient will move toward the root, not because the water is flowing, but just because of the difference in concentration of the chemical in the water. That's diffusion. Root interception is the case where you have these tiny roots, and we'll have some pictures of root hairs, but anyway, very tiny roots typically, and into which the water and the nutrients flow. And this is where the roots actually come in contact with the ions. And although I said the root hairs are where the water enters, root interception does not deal with the flow of water so much as actually the roots coming into contact with the ions directly. So the ions are not flowing toward the roots. The roots just contact them. Mass flow, on the other hand, indicates that water is going into the roots because of evapotranspiration, and it's going to eventually go out the leaves. And in the process, there are ions that are swept along with the water, and so they enter the roots that way. Now, here's a little further discussion about that. And if you have a really good memory, you might remember some of these things, but it's in the book. Certain nutrients are taken up primarily by mass flow, and others are taken up by root interception and so on. And so the ones that are listed here: boron, calcium, copper, magnesium, manganese, molybdenum, nitrogen, and sulfur, are the ones that are primarily taken up by mass flow. So of the major nutrients, if you think about it, let's see, which were the three major nutrients? Only one of them is here, and that's nitrogen, that goes in by mass flow. And remember, that's primarily nitrate that's in the water. Now, diffusion of a nutrient is, remember, that's where it goes from a high concentration to a lower concentration, is important for the other two big ones, the two major nutrients, and that's phosphorus and potassium, and somewhat for iron and zinc. And then the uptake of calcium is enhanced by roots intercepting the calcium on the clay particles. So really the nutrients move quite differently. And this gets to be important in terms of, what do you try to keep in solution, and how dense the roots are, how healthy are the roots. Here's a question that moves you back in time a little bit, or at least back to a few slides prior. And that's, what are the formulas for ammonia versus ammonium? Take a look at them at the very ends of these two words. They're slightly different. Ammonia is what you smell. That's a gas, NH3. Not only smells, but it'll burn your nose, and it can be somewhat toxic. It'll even burn leaves, for example, if you have too much ammonia gas going out into the air if you're fertigating with it. And ammonium then doesn't smell until it converts into NH3, if it does. And that's the NH4 with a positive charge. And then we have the other chemical symbols that you'll see throughout the book and throughout this series right here. There's potassium, and that's a K with a positive. And some people say potash in some areas. That was a potassium. Phosphorus, then, if you notice I have P here, and there's really no charge on it. But really, the way it's almost always found in fertilizers, it's a PO4 with a -3 charge. So those are the other two major elements. Nitrogen was the first one. And then we have the minor elements. Now, just because they're minor doesn't mean that they're not important. It just means that the plants don't need as much of these for uptake as the major elements, but they can be just as important. Calcium, you'll find out, is extremely important in terms of what percentage of the cation exchange capacity is occupied by calcium. It can really influence fertility and the structure of the soil. So yeah, it's a minor secondary element in terms of rate of uptake for plants, but it's a really important element. Then we have micronutrients, and the big one is chloride. We don't put too much chloride on. In fact, chloride with much of a concentration is toxic to plants, and different plants respond in different ways. Some plants are really sensitive to chloride. And one thing is, don't get this mixed up with chlorine. Chlorine that we use in drip systems to keep them clean eventually converts to chloride. But chlorine is different. It has a little different chemical structure, and that can be really toxic at 4 or 5 parts per million. Chlorine can be toxic to quite a few plants. The micronutrients then, again, are essential nutrients, but they're just required in very small amounts. And so we have boron, which I mentioned before is often toxic at very small concentrations for some crops like almonds, citrus. Then there's molybdenum, copper, iron, manganese, and zinc. And there are some really good books around, like there's a Western Fertilizer Handbook and other sources that will show you deficiency symptoms for specific crops. Like this particular leaf will turn green in the center and yellow on the outside, that sort of thing, to help you diagnose these. Those are just visual symptoms, and obviously plant tissue analysis will tell you about the concentrations also. So a little bit of a review. Salts are molecules that dissolve in water, but they go one step further. They dissolve into charged particles called cations and anions. So everything that dissolves is not a salt, and of course not all salts are fertilizers, but the fertilizers that we use are often salts, and like there's the calcium nitrate there on the left, and then potassium nitrate, potassium sulfate, which interestingly that one is not really super soluble, but people buy it because of the cost. And then take a look at the last one, ammonium, and there are 3 ammoniums there because those are 3 positive charges, if you have 3 of them. And then phosphate. Phosphate, if you recall, has 3 negative charges, so that balances it out. So the most common fertilizer that we use in agriculture that's not a salt is urea, but it converts eventually to a salt in the soil after the urease enzyme works on it. Remember the major, we call them major fertilizer elements, are N, P, and K, and there are a lot of minor and micronutrients. A fertigation book can't cover everything, and salts are a major problem in Western agriculture, and I've even seen it in the tropics. And what you see here is obvious salt damage. You can see the white on the tops of the furrows. This is a furrow irrigation thing, and what it is the water moves up to the top of the furrow by capillary action, and it evaporates off and leaves the salt behind, which isn't really great for plants. Now, once the plants get going, and they're a little older and the roots are down below, that salt may not hurt it. But in this case, you can see it really hurt the plants because there just aren't plants. How's that? And that's typical of really bad salt problems, is you have scattered growth like this, and obviously you want to stay away from it. And the reason I'm bringing this up is because many of our fertilizers are salts. But the thing to keep in mind is that, yes, our fertilizers are salts, or they turn into salts, but the sheer impact of the irrigation water is really what causes pictures like this. In a lot of our waters in the United States, we have quite a bit of salt actually in the water that we use for irrigation. So the fertilizer salts are rather minor compared to that, typically. Now, what you see on the right is, let's see, pistachio trees, and there are 3 rows of drip hose, and you can see a little salt on the top, and you can see the salt on the edge of the wetted area, and you see some brown color. The brown is usually caused by sodium bicarbonate, and it sort of burns the organic matter in the soil. But anyway, it doesn't look very good. And fortunately, pistachios are pretty salt tolerant, one of the most salt tolerant trees that we have. But if you look at the table over here on the left, it gives you 3 water sources. One is the Sacramento River, it comes from Northern California. And then the next is the California Aqueduct. And then the next one is the Colorado River. And if you look at the second column, that's pounds of salt per acre per year applied with irrigation water. Now, that depends on how much water you apply, and if you notice below it says that's for a typical 3 acre-foot per year application. And obviously that depends on the exact location, the climate, and the crop and all that, but you know, it's a comparison. It's apples and apples. The Sacramento River originates up in Northern California, and it comes from the Cascades, the Trinity Alps, areas like that, and that's basically rock. And you have water coming in from the Feather River that joins it, and the Feather River also has granitic type rocks, and so there just isn't much salt coming out of those rocks, and so that's why the low number of 700 pounds of salt per acre per year. Still a big number, but it's not really typically a problem. The California Aqueduct runs down the western side of the San Joaquin Valley. It picks up water from the delta, and the delta is much saltier for a variety of reasons. One is that it's at the tail end of several rivers, and the rivers bring salt down with them from irrigated lands, from return flows. But also the delta itself is salty just because of the influence of the San Francisco Bay. So bingo, the number goes up quite a bit. And then you get over the Colorado River, and the Colorado River is supplied by a lot of Colorado and areas that have sedimentary rock. And the sedimentary rock, let's say if you go up to Grand Junction, you know, that's where this oil shale comes from. In other words, it's old seabed, completely different from the granitic soils that supply the Sacramento River, which have no salt. But in Grand Junction, it's clay loams and such like that. But think oil shale, think salt. There, then, when people irrigate, that salt was already in the soil in many of those cases up there, and it's washed out, leached out, and shows up as return flows in the river. And then the people down in Imperial and Blythe and in Mexicali Valley experience pretty high levels of salinity. So the degree of the problem with salt depends on where you are, where you get your water from, if it's a well, if it's a river, you know, where the river came from. But numbers can be pretty big. But the bottom line here is we usually don't create huge salt problems in fields with fertilizer. It's normally it originates in the irrigation water itself. Now, the last sentence here on the left says that salts in irrigation water remain behind in the soil when the water is taken up by the roots, or in this picture what you see is it's evaporating off, and so the salt just stays behind. So the water goes into the roots, and not a lot of salt goes into the roots. It stays behind, and basically it makes it more and more difficult for the roots to take the water up as the salt becomes more concentrated. So again, a little bit of a review here. Most of the salts are not from fertilizers, but any salts that are in the irrigation water that aren't taken up by the plants remain behind in the soil because the water that goes in is more pure, the water that goes into the roots. So what happens is the salt will eventually accumulate and eventually has to be leached out of the water, out of the soil with irrigation water. And this, of course, is the old story behind the ruin of areas in the Middle East and in areas of California where the soil just gets saltier and saltier, and if you try to leach it out, sometimes there's no place to put it, that leachate water. And what does leaching mean? Now, this is not L-E-E-C-H, that's a creature that sucks blood out of you. This is L-E-A-C-H, leaching. It means that extra water percolates downward through the soil, and it may be intentional, it may be unintentional. It may be intentional if you're trying to wash salts out. It may be unintentional if you really didn't want that water to leave. But anyway, it goes down through the soil. In other words, it's more water than the soil can hold, and it drains or exits below the root zone. And of course, it carries salts with it. In the bottom of the root zone is where we tend to have high concentrations of salt, so because every time you irrigate, some of the salts move downward, And so when it leaves, it's pretty salty. Some of the salts are harmful, but the other thing is that if you have too much depercolation, you have too much leaching of your fertilizer, and specifically nitrate. This little image here shows you that leaching can occur either from rain or irrigation. And it depicts a root zone. The root zone is a zone of soil that has active root growth in it. And so it percolates down, carries some salts with it, and those are those blue arrows you see coming out of the bottom there. Now, to get a little more complicated about this, we have some more terms here. One is the hydrogen ion, that's an H with a positive charge, and you'll find that on the cation exchange capacity, and it's associated with acids. Then there's what we call the hydroxide ion, or OH. Anyway, it's OH with one negative charge. And something you hear a lot about in some areas where we irrigate are carbonates and bicarbonates. They're found in high pH water, and they do nasty things in terms of preventing water from going into the soil very easily. So they're found again in high pH water, and even though, interestingly enough, we have carbonic acid, but it's found in high pH water. So it's a little kind of confusing here, because when you see the word bicarbonate, you'd think that was two of them, you know, but instead the item with the -2 is called a carbonate, and the one with one charge is called a bicarbonate. But hey, that's somebody else made that up. So these are other things I'll talk about here, dealing with pH and eventually with infiltration problems. Again, this is just a primer here about some of the basic things that you run into with fertigation and trying to have good water quality and so on. One is this term pH. There's a technical term, it's called the negative log of the hydrogen ion concentration, you know, if you were a chemistry student. But here's what it really means. Acids have a low pH, and neutral is 7, if you notice here. So acidic means that the pH is less than 7. And what it really means is there are a lot of hydrogen ions in the water, relatively speaking, compared to the hydroxides. So a low pH you probably associate with orange juice, battery acid, stuff like that, you know. Orange juice doesn't burn your hand, but battery acid sure does. Sulfuric acid will really, well, it'll remove parts of your body. Bases have a high pH. That means the pH is greater than neutral, greater than 7. And we have a term we use sometimes called alkaline. And some people say, oh, that's alkaline soil or black alkali soil, but there's some reasons for that, but usually it means that there's a lot of sodium and the pH is greater than 7. And it turns out that plants and nutrition and all that, everything seems to work better with the neutral pH. There are exceptions like blueberries. You know, there are a few exceptions where plants grow best in an acidic environment, but most of the plants do best with a neutral pH. And that means the hydrogen and the hydroxides are balanced, so it's a pH of 7. And the plants just don't do too well. You get toxicities with high and low pHs. You get unavailability, which is exact opposite of toxicity. Toxicity of a nutrient means you have too much. And if you have a deficit, you know, you don't have enough. And you'll see this later on. There's a kind of an optimum area, and that's a neutral pH. And here's the thing: you can control the water pH fairly easily, and you can also influence the pH of the soil. This slide deals with trying to manipulate the pH of your water and or the soil. And now keep in mind, whatever you do with the water is going to have an impact on the soil. And the top up here begins with what most people already know about, and that is if you are surface irrigating or if you're sprinkler irrigating and you can get your equipment off the field and you have an acidic soil, it's common to apply lime. That's calcium carbonate. It's a real white substance. It can be very pure, and if it's in, really almost like a powder and you disc it into the top 6 inches, you can change the pH. In other words, what happens is you increase the pH. If you had acidity, you get rid of it. That doesn't work well if you try to do it through the irrigation system, for a simple reason that calcium carbonate doesn't dissolve. Not very well. It does eventually. We know we have limestone caverns, but it doesn't dissolve sufficiently well in the irrigation water. So if you try to inject that stuff, you're going to send little rocks through, and they just play havoc with microsprayers and sprinklers and emitters. They just plug them up, or they, in the case of microsprinklers and regular sprinklers, what they just do is it's like a kidney stone, you know. It just hurts them a little bit, and it kind of wears them out. Makes big holes out of little holes. Now, we do inject acid frequently into irrigation water in the western U.S., and we do that to lower the pH because the pH of the irrigation water might be pretty high. And then what happens is that influences the pH of the soil. Then we have nitrogen fertilizers that are often have a transformation in the soil, and almost always what happens in that transformation is the microbes tend to release acid, hydrogen ions, and so nitrogen fertilizers tend to acidify the soil. So what you have is, it's easy to put acid in, it's easy to acidify the soil with nitrogen fertilizers. Basically, it's easy to lower the soil pH, but it's a lot more difficult to raise the pH of an acidic soil if you have drip irrigation that is on the surface, and that you can't, you can't disc anything in. For example, trees and vines. You just don't do it much. Now, some people do apply lime on the soil surface with permanent crop drip, and I really don't know exactly how effective it is, but sometimes they don't know what else to do. Anyway, you have to be careful with your fertilizers and the acid that you don't create a lousy chemical condition for your roots and for nutrient availability in the wetted areas of drip. The images on your left show you two common ways to acidify water with acids. The first one here on the left, this shows you this orange container right here. Inside of there is an injector pump. It's an electric pump that has specific design with the gaskets and so on, that it can handle sulfuric acid. Sulfuric acid is kind of nasty. Infuric, by the way, that's urea sulfuric. It's pretty nasty too for some injection pumps. You really have to get a pump that'll handle those types of acids. But what I'd like to point out here is that the tank on the inside here, and that's one of the points, it's on the inside of an outside tank. It's setting down in it. That's the one that has the acid in it. And what they have is a safety tank on the outside. Now, there has to be a way, if you notice over here on the left, there has to be a way to get through this outer wall to the inner wall, and you have to be able to access the hose, to be able to shut it off and things like that. So you have to have some room in there between this wall and the tank. But those are details. But this gives you an idea of the type of thing you have to deal with sulfuric acid. You need a special pump. This has to be locked. Generally, certainly in California, farmers themselves don't set up the pump, and they don't adjust the pumps. They hire companies to do that, who bring out the sulfuric acid, they handle the tanks, they fill it up, they make all the connections, they have the pump, they calibrate it, and they take care of all the acid stuff, simply because of danger. Now, there's another form of acid that also has sulfur in it. Now, if you notice, this is a little different. This is called sulfurous acid. See the word sulfurous as opposed to sulfuric. And if you notice, they both have two H's in them, but the last part is different. This is SO3, this is SO4. Whereas the SO4 is a strong acid. In other words, sulfuric acid is very strong. This is what is known as a weaker acid. That doesn't mean it's bad. It's just that if you put your hand into this stuff and you pull your hand out, you still have virtually all your skin on there still. If you put your hand into this stuff, sulfuric acid, you don't pull much out. So for a variety of reasons, which are discussed in the separate video on SO2 generators. People have these machines. This is actually a burner here with a chimney, and there's elemental sulfur here. Here are the bags of it. They dump it in this container. They light a fire down here, and they mix water with it, and out comes sulfurous acid. How's that? So we call it an SO2 generator because when this stuff burns, it makes SO2, sulfur dioxide, which of course is toxic. But somehow if it gets mixed in just right with the water, it makes this stuff, sulfurous acid. And this is almost virtually always operated by farm employees with some safety instructions. So anyway, those are two common acids that are used in irrigation water. Then there's the soil itself, and we just have one slide left on this one. Remember the clay, not the sand particles, not the silt particles, but the clay and the humus, which means old organic particles in the soil, have negative charges. And that's where we have what we call a cation exchange capacity. They have negative charges, so they attract and store on their surface, not inside, but just on the surface, just like a magnet. They attract cations like ammonium, potassium, and calcium. And most of the anions then are just found in the soil solution. So there's a pretty nice picture of a root there. How's that? So this concludes the second video that we have. It's all prep work for the rest of it. In other words, trying to explain some basic concepts. Hope you've enjoyed it, and see you for the next, well, there's a total of 25, so see you for quite a few. Goodbye.